happens when we put an object into an external electric field, and the headline is, of course, electric fields in matter. And now, first, let's just briefly look at what types of matter we have. And they're typically divided into three categories. First of which is metals, or typically good conductors. And then we have the not good conductors, which are insulators. Finally, there's this weird class of matter called semiconductors, which we won't be discussing much, but which has its own funny properties. Now, in electrostatics, a semiconductor has some conductivity. So for electrostatic purposes, it will be similar to metal, because at finite temperatures, it has some capabilities to conduct electric currents. Okay, so let's look at this question for these classes of matter, and we'll start off with the metal. So let's see. Yeah. So the basic setup is like this. We have some objects, which is now a metal. Inside the metal, the field must be zero always. I'll explain why. And we put onto this object an external electric field. For instance, we could put it between two plates in a capacitor, and then insert this object and see what happens to it. Okay, now, so what will first happen is that as we turn the external electrical field on, the charges will start moving, because inside a metal we have free charges which are allowed to sort of roam around inside the material. And of course they will go, the negative charges will go against the field lines. So they'll end up on this side of the object. And the positive charges will follow the field lines and go to this side. And now the charges will keep moving around as long as there are electric fields inside the material. And this means that eventually they will set up an electric field which exactly cancels the electric field from the outside. So there's no field inside in the electrostatic regime. So I guess this should be pretty intuitive, because as long as we have fields, the charges will have to move around, and then at some point they will just how to say it? It will make the external field go outside the material only. It will just negate the effect of the external field inside the material. And now, of course, this means that we get a boundary condition from this. Because if there's an electric field component parallel to the surface, well, then there would be a current on the surface. So this means that the parallel E field has to be zero on the surface of the metal. And the potential has to be continuous. So that's another one. This typically means that the potential is a constant inside the whole material. Otherwise, you will get, if there is some variation in V, you would get an an electric field from that. So now, what if the object is dielectric? Well, inside a dielectric, typically plastic, glasses, wood, everyday stuff that doesn't conduct electricity, the charges are not allowed to move around because they're bound to specific atoms or molecules in the material. So there will be no currents. So let's see. Start here. So if you have the same setup, we now have essentially the same thing, that the negative charges will move slightly towards the field, and the positive in the same direction as the field. But now, as we can't move the charges, they're actually stuck to the actual atoms and molecules, we'll get an electric field inside the material, even if we can, to some extent, negate the effect of the external field. So if we have that the dielectric function inside is bigger than the dielectric function outside, this could then be air or vacuum, so it will typically always be bigger, sorry. Then we will get that the electric field outside is stronger than the one inside. So I'm just going to sketch now as an example. If you have a sphere in an external uniform field, what the field lines will look like. So far away from the sphere, the electric field is not going to change. Now, if you're close to the sphere, the electric field lines always have to be orthogonal to the surface, right? Because if there's a parallel component, you'll set up a current, which will eventually negate the field. So it's going to look something like this. So here we can actually just see the boundary condition. And of course, inside the metal, there's no field, so there are no field lines. Now for the dielectric, you get the same at sort of far away. You have no change in the E field. But if you get closer, the field lines will do something similar, but not quite be able to eliminate the field inside. So you get something a bit similar. And inside you get a constant field. And actually for the metal, because this is funny, because as we always have to be orthogonal, there's a field line going like this. Which you won't get here, of course. So here you see inside the sphere, it just happens so that the electric field is constant, uniform, inside the sphere as well as outside. So now, just as a small reminder, let's recall what the dipole moment looks like. We saw this last time. So this is if you have a continuous charge distribution, you integrate over the contribution from all charges, or in the discrete case, you just multiply the separation vector by the charge. Like this. And now, if you look at small atoms, they will also polarize when I'll talk more about it in a second. They will polarize when you put on an electric field externally to the atom or molecule. So then we get a polarization that's proportional to the electric field, like this. So the alpha is the polarizability, which is then a constant for the material. And let's see. Yeah, and if alpha is large, then the material is easily polarized. So you see, for a small electric field, you get a large polarization out. And the polarization then becomes this dipole moment. So, yep. Let's see. First, I'm going to talk about, well, the polarization mechanisms. And there are basically two different mechanisms that occur inside the material. And one is that you get induced dipole moments on the atom due to the external field. And as I'm sure you learned in some chemistry course, some atoms or molecules in particular can have a built-in dipole, let's say sort of chemically. And in these molecules you could orient them along the field to get a net macroscopic dipole, a net polarization macroscopically. So if you look at these mechanisms inside the material for some example atoms, I'm just going to sketch this to give you the idea. Let's just look at a helium atom, which you can find in helium gas because it doesn't react too much chemically. So if you have no external field, you have a plus charge at the center, which is the nucleus of the atom. And then you have an electron cloud swirling around, which has the, it has a negative charge density, such that if you integrate the charge density, you of course get the opposite charge. So there's no net charge here. The monopole term is zero, so to speak. So, but if I now apply an external electric field to this, the plus charge is going to go along one direction of the field lines, and the negative charge is going to go in the opposite direction. This means that now the plus charge in the center is not going to be in the center anymore. This is, of course, exaggerated, so that we now have some distance here that we move the charge density, roughly speaking, so that we get a dipole moment, which is somehow proportional to D and Q. Like this. So the bigger the separation, the larger the charge, the more dipole moment you get in this polarization. So this is an example where you would get typically, this is typically an isotropic material, because if I put the electric field in this direction instead, like this for example, you would get the same response, so to speak. So this is an isotropic material. But now what if the material is not isotropic? For example, you could look at the CO2 molecule. Like this. And now if I apply an electric field in this direction, what would happen? Can anyone imagine? Any suggestions? Okay, the funny thing now is of course that it's easier to polarize the molecule in this direction than in this direction. So the polarization might not be directly proportional to the electric field anymore. And this is an example of an anisotropic material. So now the alpha over here. Let's see. I think I killed the alpha. Anyway, the alpha is no longer. No, here it is. This is not any longer just a constant of one value. Rather, it's a tensor, a rank 2 tensor. So now we have to take into account for each component of the polarization vector, we have to take into account each of the components of the E field. And the alpha is a rank 2 tensor. You can tell it's rank 2 because it has 2 indices. And now if I write out this sum, you get alpha I1, E1, and so on, like this. So for each component of the polarization vector, you get a contribution from, in principle, all the components of the E field. And now the P vector is no longer proportional to the E field. It's no longer parallel. And I'll denote this by this symbol. So any questions about that? Okay. Now let's look at the other main effect which causes polarization, and that's the orientation of microscopic dipoles. As an example, I use hydrogen chloride. You know hydrogen chloride, it's saltsyre in Norwegian. It's very strong acid. It consists of a hydrogen and a chlorine molecule, and the chlor tends to grab the electrons from the hydrogen, so that this is a polar molecule. And I'll write that down by setting a small minus here, and a plus here. And now what happens if I apply an external electric field? Oh. So I apply an electric field, and of course the chlorine is highly attracted to it. So you get a negative, well, I call it F minus. It's pulling in the negative direction of the E field. And the hydrogen sees the positive force that is in the direction of the E field. And so you get these forces, of course, balanced because there's no net charge here. But they don't, well, if the center of mass is somewhere here, it still adds a torque. Like that. So now the molecules in the gas will start to try to align with the E field. And this effect will have to compete with the thermal collisions between the gas molecules in the gas, because they keep bumping into each other typically. So the E field will try to align the molecules, and the motion inside the gas will try to make them point in any direction. So there's two competing effects here. So as we increase the field, you get more and more polarization, and it sort of wins over temperature. So this is actually something you could investigate using statistical mechanics, because now you need to sort of figure out what are the energies I get from turning the molecule this or that way, what's the probability of being this and that way for a certain temperature, and then you can see how the temperature affects the dielectric constant of the material. Now, of course, we're not really interested in what goes on at the molecular level, because I'm interested in making a large piece of material like plastic for a wire or some such, and so we need to go back to the macroscopic level again. And then we exploit that the dielectrics contain a huge number of atoms and molecules. So we get essentially the sum of these. So I'm just going to write down a formula here. And I will just write it like this. I'll put this small line here to indicate that this is a large P, and this is the polarization, and this is the dipole moment from a small region around R. And I'm going to average over a small region because, well, as you know, the mass density, for example, of material, we're not really interested in the mass density in detail, because inside the nucleus of an atom, the mass density is enormous, and outside it's almost nothing. So we're interested in the average over, let's say, a few thousand molecules or a few thousand atoms. So in the same fashion, we're going to look at the dipole moment from a small lump of molecules or atoms, and the polarization in the same way. And this is called a macroscopic field. So we don't care that inside the atom the electric field is very complicated. We're just going to look at sort of the macroscopic average, because after all, this is classical electrodynamics. And if you're going to be bogged down with investigating every atom in a gas, you will never be finished doing anything. So just to write down what this is again. This is a dipole moment at R. This is the dipole moment of atom or molecule of type I. Let's say I have a solution. This is chemistry. So if you have, let's say you put water and alcohol inside here. Now these, of course, have different polarizabilities. So I will need to sum them up. So if you have a bigger material, a more complex one with several types of atoms and molecules, you need to just add them up. So the N is then the average density of the atoms or molecule of this type at point R. So if I'm here, there's a certain density of the material. This is the number density of these little dipoles of mine. And now this average is over a small region close to R. So this is just to give you some idea of how you could, if you knew the microscopic properties of the material, of the atoms on the molecule, so to speak, perhaps obtained from quantum mechanics, then you could extrapolate the macroscopic electric properties of the material. And the macroscopic polarization, which is this big P, is defined as dipole moment per unit volume. And as you see, you have the little p's are dipoles, and the n is a number per volume, so it ends up at the correct unit. And now, after I remove some of this writing, we're going to define a new field which will take into account the effects of polarization as well as the external electric field. So, and this field is of course the electric displacement field. And it is defined in the following way. It's first the electric field, and then we add the polarization. And this now forms the so-called constitutive relation, which we'll be discussing in a few minutes. So the idea here is that we take the electric field and we add the effect of the polarization so that we get a new field, and we hope to obtain simpler equations for this than from these two. Because now if I start out with a material and I apply an external electric field, it's going to induce some polarization in the material, which is going to make an electric field pointing in the other direction. And then this is going to change how much the material is polarized and so on. So it's hard to this is sort of a chicken and egg problem. Who came first and how does it affect the other? So instead we try to get rid of this problem by defining a new field and see if we can find some interesting equations for this field instead, which are more convenient. And now as you can see, the D field has the polarization built into it. So it's very nice for working inside materials. And what equation does it satisfy? Whoop. And the brief answer is just that it satisfies the Gauss law. This F stands for free, so we call this a free charge density, and I'll get back to that in a few minutes. So it's the charge you've been thinking about before, essentially. So yeah, this one does not contain the induced charge densities which you get. I mean, you saw the molecules, right? So if you align all the molecules in an HCl gas, they get sort of the pluses point to one direction, minuses to one direction, so you get some bound charges. These are not included here. Not the charge is bound to the molecule. I hope you can see that. You can see it? At the bottom of the blackboard? Okay, no one's complaining. So now I'm going to motivate why this is the case. And now it gets a bit technical, but we'll just have to get through it. So, of course, as I said before, the external electric field will start inducing atomic or molecular dipole moments in the dielectric. And I'll just remind you again, if I have it here. Yeah. For a dipole, the potential looks like the following. Like this. So if I put a point dipole at the origin, this is what the potential looks like. And I'm going to use this in my let's see, well, proof. It's not a rigorous proof, but it will motivate why this is the case. So I'll start out by writing the well-known formula for the potential from a free charge distribution. And now, of course, I have to add the dipole contribution locally. So this is another integral. And it's essentially a sum of small dipoles, like the one we see over there. So this now is the potential from a small point dipole, right? These are the dipole moments per volume multiplied by a small volume element. And of course the distance cubed. In the denominator. So now we just add up the contribution from all the charges and all the small tiny dipoles inside the material. And now we're going to do some tricks here. So first of all, I'm going to rewrite this r minus r divided by r minus r prime cube. And I can do this in the following way. Now this is just a gradient of 1 over r. And I'm going to put a small prime on the gradient here to show that it's the gradient with respect to r prime. So we don't differentiate with respect to these coordinates, but with respect to these coordinates, because the r vector is now, of course, a constant inside the integral. Otherwise, I won't get out the potential, right? I'm looking at one point r vector. So this doesn't change. It's a constant from the point of view of the integral and the differentiation. Okay. Well, let's do that. This term stays the same. And now I take the dot product here with the gradient of 1 over r. This is, of course, a vector due to the nabla. Now I'm going to try to change this to become a gradient of the p by partial integration. So this turns out to in the following way. Again, this term stays the same. So by partial integration, I move this to be in front of the p, and the surface term will vanish because we're integrating over all of space, and because, well, I have a piece of material here localized in space, and then at infinity, at the edge of the universe, there shouldn't be much contribution to the integral. So that term is just set to 0, and then we end up with this. And now the final step is to gather these two integrals into one. I think I'll just do that and then explain why. Let's see. So first I have the charge distribution. And then I have a contribution from the gradient of the P field. Now the funny thing is this looks like a charge distribution, doesn't it? I'm just going to call it rho bar. It has the units of charge distribution, and if I do this integral, well, if I told you this was the charge distribution, you would just do the integral, you would find the potential V, and we all be happy about it. So this is interesting, right? This is what we wanted. And now I'm going to use the following definition. The gradient of this beast is now the electric field. And if you remember let's say the standard formula for V, it was just this term in front here, right? But now if I say that rho bar is my charge distribution, then I know what, and I know this equation, then I know how I can connect the E and the rho bar. And of course it's the following. It's the Gauss law with a modified charge distribution. And if I write it out, yeah, I could put an F on these rows because there are the free charges. And now I see that if I move this around, I can of course obtain the equation over here. And this is because, well, I'm just going to grab a small box of space here so we get this finished before the break. Yeah, if I just multiply by epsilon and then move the terms around, I get that lambda times epsilon and the E field, the first term, the term on the left, and then the P field I move on the same side, is equal to the free charge distribution. And now this is of course the D field. And it's possible that the first guy who thought of the D field looked at this equation and said, well, I got a new field here, which is, why don't I solve the equations for that field instead? And I think that's a nice place to stop for questions before the break. So, what are you wondering about? I'm pretty sure someone has a question about some mathematical trick or. Here? You're right. There's no absolute value here. This should be a vector, of course. Yep. Any other errors or comments or questions? This one? There's some misprint somewhere? Yeah. Yeah. But there's a minus sign here. There should be one here, yeah. Thanks. So, that's correct. Anything else? Okay, we start again in 15 minutes.